All right, so for 5.2, we're going to go over a different kind of distribution. We're going to go over the binomial distribution, which is different than our normal distribution. So, what a binomial is really looking at is this idea of only two options, binomial, by two options from your survey or your sample from whatever population. So, our key focus is finding the probabilities using this distribution and kind of looking at what it is. Okay, so then let's look at the definition. A binomial probability distribution results from a procedure that meets these four requirements. Requirement one is you have a fixed number of trials. So I've done this, I've surveyed 100 people. I've done flipping a coin 30 times, like a fixed number. You're given that a number. It needs to be independent, means one trial doesn't affect the other. So if you are saying without replacement on anything, then it's not independent, it's dependent. So it wouldn't meet the requirement. Okay, if so we really wanted to say with replacement. Okay, with replacement. Is that kind of that idea of two? Problem three says, and this is the big idea, each trial must have an outcome classified into two categories. Commonly, it's success or failure, yes, no, true, false kind of things. Okay. So, last thing is the probability of the success remains the same in all trials. So the probability stays the same. That kind of goes with independent and dependent, right? Because, like, if you're independent, one doesn't affect the other. So each trial had the same probability. So let's look at the notation. S and F, just success, failure. If I say the probability of S or probability of P or whatever is just the probability of success. So we typically call that P. So the probability in favor of something. It doesn't necessarily mean it was like successful, right? We could be testing of something that's, you know, I don't, they have a caution in here about it right here. It doesn't mean it's true. It's just the word we use is success. Okay. And then one minus that probability is that Q value, failure. So against or for whatever you're looking at. Okay. N represents the number of trials. And X represents the specific number of successes in the trials. So X can be a whole number, 0 to N. So, like, if we want to know, if we surveyed 50 people and we want to know exactly, and this is the probability X, like three of them, what do they think? It'll make more sense when we look at a problem, but X is just that number of successes. Okay. I don't think I said that very well at all, but let me look at an example and I'll get it out a little bit better. So our P and Q become what we use instead of S and F really. And X is that probability of whatever number X trials. That's what I was trying to get out. Okay, and this kind of just says like be careful, read through that we're not really, we call them our successes, but that doesn't necessarily mean what it is. So let's look at an example with Twitter. So when an adult is randomly selected without, or excuse me, with replacement, so it's, with replacement, that's important. There is an 85% probability this person knows what Twitter is, okay, based on whatever survey. Suppose that we want to find the probability of exactly 3 of 5 randomly selected adults that they know what Twitter is. Okay. So is this a binomial distribution? So let's go through our requirements. Okay. So is there a fixed number of trials? Yes, 5. We are picking 5 people and we want to know if at least 3 of them know of Twitter. Okay. The trial's independent. Yes, with replacement. Meaning, they're all in there each time I pull it out, our sample. Each trial must have the same number of outcomes with two categories. They either know what Twitter is or they don't. So yes, we're good there. And the probability remains the same. So yeah, this is an example of a probability distribution. Yes, we went through each of those. And yes, this is one. If the procedure does result in a binomial distribution, identify each of the following. So I put the solution here mostly because some people, are taking this class online, and it's nice to have the solution to at least one of the problems. But our number of trials is 5. I'm not sure where that plus sign came from in there, but just a typo. I wanted to make sure you knew the positive, that n was positive. Okay, and then what was our x? Well, in this problem, it says you want to find out that exactly 3, that is our x, like 3 people knew of Twitter. It's kind of like what I'm asking about. It could be like greater than 3, less than 3, or equal to. Okay, and then, or it could be greater than or equal to, or less than or equal to. So I guess there's that option too. What is the probability in favor of knowing Twitter? Is 85% or 0.85. So the probability of not knowing is the 0.15. This one, right, is 1 minus p. These always add to 1 because you only have 2 options, right? You either know Twitter or you don't. Probability for, probability against. Okay, so that's like some of your homework problems will look like that. You're basically going to decide if you can do a binomial distribution, and if you can, what are your notation or symbols? What are the numbers that go with them? Then we have this rule that like we can treat dependent events as independent and like use our binomial distribution stuff. If 5%, it's called 5% guideline for cumbersome calculations. When a sampling without replacement, so we don't meet the requirements, right? And the sample size is no more than 5% of the size of the population. So it's a really, really small percent of people that you're picking from the population. Treat the selection as independent, even though it's not really. So basically, I can use my rules. Okay, so that's kind of cool. We always have we have some of these in normal too. It's like, oh, well, this calculation's so terrible. Let's just pretend that it's a binomial and we will use this. It's close enough. It's kind of that idea there. Okay, with that known, let's go into what the calculations and what we can actually find for those probabilities of a binomial. So here's method number 1. Check out my formula. Again, we have our variables here, and it's saying like, in factorial, remember that's counting down, right? So if you have 5 trials, it will be like 5 times 4 times 3 times 2 times 1, so forth. So this is the formula for finding a probability of a binomial. And here it is for Twitter, right? So 5 factorial was our number. We wanted to know for 3, we would put 5 minus the 3 times the 3 factorial, because up here, I think I can make this smaller so we can see both. Yeah, there we go. So our n is just our number, right? And then our x is in 2 places. So here's our x and our x. N minus x. Hold on. Okay, so by the time you see these notes, I will have fixed this. I copied this from the PowerPoint, and I didn't notice that this is switched until we looked here. Notice that it says x minus n, and then I did n minus x. This is n minus x. So I stole that little piece from their PowerPoint and didn't even notice that they had a typo. It is your total minus x. So please fix that. But again, by the time you watch this video, I will have fixed that on your note packet. Okay, so Sorry for the pause, but I was like, wait a second here. Why do they have that written wrong? So what we're going to do is we're going to do, again, with this formula, we're going to do the n minus 1 and then the in or the x out here, n minus 1. I can't even say it right. Um, n minus 3. And then our probability times our probability of the 5 minus 3. This is terrible. It will get me the answer. Someone wants to try the formula. Great. Let's look at method 2, right? Our method 2 says, let's just use StatCrunch, right? And find that for us. So yeah, there is a typo, but in the long run, I would prefer you just use StatCrunch. And so if you look, I did some little things here for you. Basically, you're going to go to Stat Calculator, and there is a binomial probability calculator for you, just like there's a normal calculator. And look at all these other distributions that we're not covering until advanced statistics, right? Or a higher level. So what we're going to do is we're going to see this is our calculator, and we can put in our number of trials, our probability, and what we're looking for with that x. Well, this question asked is x, what's the probability when x equals 3? And you could change this to be what if it asks like greater than 3, less than 3, or whatever. It has all those options in there, and it gives that same answer as we got with the formula, about 13.8% or 0.138. So kind of cool StatCrunch. The other thing is you have a couple more formulas. There's no typos on these ones. Okay, so we could find the mean. We could find the variance, which we don't look at variance much because it's just something covered in the higher level. And then the standard deviation. I mean, variance is really just like, like looking at how different things are, kind of that idea of being away from the mean. Similar to standard deviation, but different. Okay. And then we care about the standard deviation, which again, we can find with this formula. We know N, P, Q, we know P, we can do that. So those formulas aside, let's answer a couple questions. And oh yes, we're going to use StatCrunch. So between 1974 and 2011, there were 460 NFL football games decided in overtime. And 252 of the games were won by a team that won the overtime coin toss. Is the results of the 252 wins in the 460 games equivalent to random chance, or is that significantly high? So really, we're really asking, are you more likely to win if you actually won the coin toss in overtime based on these results? So I'm going to do a split screen. I'm going to open up StatCrunch. I think I have it open in here. No, StatCrunch is, and I'll just close whatever's on there. Hold on, quick, logging in. Thought it was already logged in on my iPad, but it is not. Okay, I mean, there's a bunch of data on this one, so close. I wonder if I could just do. Here we go. I don't want you to see a bunch of data. Okay, so where we go for this, if you look at your notes, you go to Stat, Calculator, Binomial. So it's a binomial calculator, looks like this. So for football, we need to put in our N, that's our number of games, which was our total, right? 460. That's going to be our total number. And we want to keep P at 0.5 because we're testing. It says like I know we see a little bit different. We're testing if it is equal at that 0.5. And then what we'll put in is we'll put in that number that we had, which was 252. And what symbol do we need if we're saying or more than? So is 252 wins significantly high? We use the answer to question to find the probability or more than 260. So or more than, is going to be greater than or equal to. There we go. And I know this gives us this weird graph of that distribution, and then it shows in red what we're looking at here. And we can see the probability is equal to 0.0224. Okay, so up here on your note packet, you're going to put the probability of 252 or more, right? That's what we did, is equal to 0.022-ish. Okay, so what does that tell us? It tells us that that is in that really high or above the 5%, right? It's in that significantly high range. So basically, we, according to our data, it's better if you win the coin toss, because this is a significantly high number of people that are winning the overtime, because that 0.02 is so high up there. Okay, assuming the wins and losses are equally likely. I think we answered all the questions. Or more games. Yep, this is just our probability. And look, we could look at what's the probability of being equal to the 252. There's that one. We could be less than or not equal to, right? So really, you can put in whatever you want here and kind of play, which is sweet. And it'll give us that probability. All right, let's look at the devil. Based on this poll, 60% of adults believe in the devil. Assuming that we randomly select 5 adults, find the following probability. The probability that exactly 3 of the 5 adults believe in the devil. So it's exactly 3. So what is our total number here of trials? Is only 5. Was very small on this one. And we were given the probability. We weren't comparing it to half-half like the last one. The last one was a little bit harder, but I wanted to show you that one. Probably should have started with this one, but that's okay. And then this one is 60, so we have that. And then we put is equal to the 3. Okay, and then compute. So I get the probability is on that one is exactly 3, equal to 3. The probability of x equals 3 is going to be 0.3456. So 34% is the probability of 3 out of 5 adults that they believe in the devil. Wonder if wonder where this 60% of people believing in the devil percent came from, but it's all right. They say it was from a Harris poll. They probably got it real data from somewhere. So the probability that the number of adults who believe in the devil is at least 2. So this one's asking for at least 2. So greater than or equal to 2. So we change this symbol to greater than, and we change our 3 to a 2 and hit compute, and that's way bigger. So at 90.913-ish. So if greater than 2 out of the 5 people, would 91% would believe in the devil. Okay, so this calculator is amazing. If it gives you a table, you don't need to use the table, use the calculator. If it gives you the formula in the example, you don't need to use the formula. You can always use this calculator, this from StackCrunch. Okay, so let's just look at a couple examples that really, do they meet a binomial distribution or not? Can I use the binomial? So I'm going to do full screen for a minute as we read through these. So the first one, if I surveyed 300 adults and I asked if they like the current president, is it a binomial distribution? Well, I asked yes or no question. Do they like the current president? Yes, no. Each person's independent. We don't have any repetitive. So yes, in general, the yes. Looking at what they gave us for information, yes, that meets it. B, surveying 100 adults and asking how many colleges they attended after high school. Does that meet the binomial? Well, when I ask everybody, they could possibly have gone to 5 colleges, right? So no, there's not a 2, right? For binomial, it's like yes, no kind of question, or this, only 2, heads, tails. So no. If I asked people, do you like math in general? Do you like math? Now, I don't have necessarily a fixed number of trials, but in general, yes. I would need to only ask so many people. Um, I mean, you really could put no because you don't have a fixed number of trials, but in general, if I have a fixed number, yes, that one would work. Okay, there is a sort method in IVF that will give you a boy, right? And it's called a Y sort. To me, this is terrible. Just have a baby boy or girl, meh. But anyway, in a lot of countries, people prefer to have a boy. When the 110 couples use this Y sort method and give birth to 110 babies, the sex of their baby is recorded. Well, it's like I'm sorting them. I have 110, so I have a fixed number. And then the birth of the babies is recorded. Well, what's the birth of a baby? Boy or girl? So this is a yes. It's a little weird, but it's a yes. Okay. 6 different senators from the current US Congress are randomly selected without replacement. And they're asked whether or not they've served over 2 terms. So the question is, if they served over 2 terms, that's a yes or no. We're good there. But where are we not good? Without replacement. So that is going to be that independent dependent question, right? They're going to be dependent upon who's left. So this is a no. Okay. If you ask the same question with replacement, then it would be a yes. So you're looking for a fixed number, which again, like C could be a no or yes. We don't have a fixed number, but we're looking for that yes, no question. We're looking for independence. Okay. All right. So one more example here, using those formulas above that said, well, what about the mean, standard deviation? Is something significantly high or low? So the mean, we go back up, sorry, go back up, looks like this here, right? So the mean is literally going to be mean of the whole population in times the probability. Number of trials times the probability is your mean. Okay. Standard deviation is the square root of n times p times q. So it's like 3 or 4 things that we're going to multiply together there. Okay, so let's do that. We'll have to find a couple things. So in order to do our mean is equal to n times p. Well, what is our n? What's our number of trials? Well, assume the hybridization, I'm terrible with pronunciation, hybridization, like when you're breaking them apart, hybrid experiments are conducted with peas having the proper for their offspring. Totally laugh at me, it's fine. There is a 0.75 probability that a pea has a green pod. Okay, assume that the offspring peas are randomly selected in a group of 52. So for this one, our n is going to be 52. Okay, what's going to be our p? It's going to be the 75. So we're going to times those together. So 52 times 0.75. And I got 39. So the mean is 39. If I wanted to know the mean, okay, the average number of pods out of the 52 is going to be 39. So you could maybe see where that might be helpful, right? If I want the average number in something, giving a probability and given that binomial distribution. It is really for higher level analysis of something. Okay. Find the standard deviation. Well, the formula was the square root of n times p times q. So our n, again, is our 52. We had 52 trials. We know our p is 0.75. Okay, and then, oops, And then Q would be the, oh, I wrote that wrong, 0.75 times 1 or minus 1. Let's write it like that. So the 0 on there would be helpful, is going to be 0.25, right? So Q is equal to P minus, or 1 minus P. You don't want it to be negative. Just remember you're subtracting it from 1. So that's where the 0.75 comes from. So on my calculator, I'm going to put in 52 times 0.75 times 0.25, and I got 9.75. And then I have to take the square root. So square root of my 9.75, and I get about 3.12. So I have the mean at 39, and the standard deviation's about 3.12. Okay, so now it says use the range rule of thumb to find the values separating results that are significantly low or significantly high. So basically, like, I'm not, the range rule of thumb, I left that in there because it says it in your homework. It's basically, we did the standard deviation above. We don't need to do any weird calculations. We already have that. We're really just going to take our mean, 39, and add 3.12, and then add another 3.12, right? And that's going to give me my high, significantly high. So 39 plus 3.12 plus 3.12 is going to give me 45.24. So anything above 45.24 would be a result that would be significantly high. Okay, so this one's significantly high. Okay, if I want low, I take that mean and I minus 3.12 twice, right? So 39 minus 3.12 is going to give me 32.76. So this is going to be our significantly low. Anything below that is going to be very low, according to this experiment that we have with the probability given, right? So you can see what's going to be significantly high, significantly low. I did not use any stat crunch for this question, right? I don't need it. So I could even ask like about a specific value. Is it going to be significantly low or high? Or if I give a probability or something like that, then you could ask, answer more questions on this. So this section really is to help you look at, there are more than normal distributions. We have binomial, that's one or the other, right? And we can use the binomial calculator technology, which is amazing, versus using that formula. So don't look at your example button for every single problem, because it will show you the formula or a table. And we really have this beautiful calculation we could do for a lot of them. All right, let me know if you have any questions.